So these are the contents of my talk, but these are also the keywords of my current research activity. And let me start this introduction saying a few words about the current status of particle physics phenomenology. Today, colliders are our best research tool to advance our knowledge of particle physics. And together with all the other experiments, they have confirmed the predictions of the standard model of particle physics to great accuracy. So this is the current picture of particle physics. However, most of the particle physicists believe that this is an incomplete description of nature, and there's a more fundamental theory should exist. Reasons to believe so are the neutrino masses, the hierarchy problem, and on the other hand, there are other reasons that are related to gravity, such as the observational evidences that favor the existence of dark matter, and also the Big Bang initial conditions. So studying particles together with gravity is another fruitful and very interesting road to advance our knowledge of particle physics, and the reason is for this is that gravity knows everything, because gravity is an interaction that between all things that have mass or energy. So anything that has a large mass, for example, if there are a distribution of many particles, they will curve the space-time, and this way we can learn about their presence. And the most notable example in the current in our universe is dark matter, and in the early universe is inflation, for example. So what is dark matter? Dark matter is a hypothetical form of matter that is assumed to account for approximately 85% of the total matter in the universe. We know this from observing the rotation curves of galaxies, but from other observations, for example, from CMB, here you see in this picture the CMB acoustic peaks that give us with a great accuracy the abundance of dark matter. And it is dark because it does not interact with electromagnetic field, does not absorb, emit, reflect electromagnetic radiation. So we can see the presence of, feel the presence of dark matter from its gravitational effect. And also you see here the picture of the Ballet cluster that is an evidence that favors the presence of dark matter versus modified gravity scenarios. So gravity tells us about the presence of a particle that is beyond the standard model, the dark matter particle. But also gravity can tell us about the presence of other particles that existed in earlier stages of the universe that are unstable. And the associated field of these particles might have played a crucial role in the evolution of the universe, and the most notable example is inflation. So inflation is the most compelling paradigm that we have in order to explain the origin of the primordial density perturbations that grew into CMB anisotropies that we see on the sky. So from examining the CMB sky, we've done this the last 3 decades, we can learn about the inflationary dynamics, the potential, about the properties of the inflation field, about the duration of inflation. And the standard assumption is that to have the so-called slow roll inflation. But I should mention here that from the CMB sky, we cannot learn about the entire inflationary trajectory. We can learn only about a small part of the inflationary trajectory. And the reason is that the CMB sky gives us information only about the very large scales, and we know nearly nothing about the small scales and how the spectrum of the density perturbations looks like, the primordial spectrum. So slow roll explains very well the CMB sky, but at the later stages of the inflationary evolution, we may have departure from slow roll, and this is something that I will talk later on, and we'll have some results to present on this issue. So now let me move on and discuss some other hypothetical fields that might also have played a critical role in the early universe. And these are the fields with M-Planck suppressed interaction, so these fields interact gravitationally. Such fields are predicted in many scenarios beyond the standard model, for example in string theory or in supersymmetric theories. And why are we interested particularly in these fields? The answer is that these fields are decoupled from the thermal plasma, and also they decay late, so they might have an energy density that is can increase compared to the radiation energy density, and might realize the so-called early matter domination era. So if they decay very late, this might be problematic, but if they decay before the Big Bang, this is okay. So we don't have the so-called cosmological moduli problem, but this might not be a problem. This might, in some scenarios, an early matter domination era is required in order to have a viable cosmology. So what is interesting with this scenario, this is what I'm going to discuss later on, is that an early matter domination era might have a visible impact on the CMB sky, on the observables of the CMB, and generate gravitational waves as well. Another basic reason to believe that there is new physics beyond the standard model is the matter-antimatter asymmetry that we observe in the universe. So in our universe we see only matter, and we see antimatter only as isolated individual particles, for example in cosmic rays. And if we assume that we started from a baryon or lepton symmetric universe, somehow we have to evolve to a universe with a baryon asymmetry. So in order to achieve the so-called baryogenesis, we have to fulfill some conditions that have been formulated by Zakharov. And one is to have a baryon number violation, C and CP violation, and also depart from thermal equilibrium. I should say that C and CP violation in the standard model is not adequate to explain the matter-antimatter asymmetry in the universe. And also mention the critical role of gravity that is important for the third condition, because thermal equilibrium, departure from thermal equilibrium happens naturally in an expanding background. So I will present later some scenarios and some models that we construct to explain baryogenesis in the universe. And let me now turn to quite different topic, but it's related to all of the things that I've said before. And this is gravitational waves. So gravitational waves is the new great, let's say, discovery, the new accomplishment of science, of physical science of the 21st century. And with gravitational waves, we have learned that, firstly, that gravitational waves exist, that black holes exist, and they are very abundant in the universe. And we hope that sooner or later, the stochastic gravitational wave background will be detected. And there are good reasons to hope so, because there will be a network of operating gravitational wave detectors that they could even detect gravitational waves from the primordial universe. And by studying the gravitational wave signal coming from the first seconds of the cosmic evolution, we can learn about the temperatures that have been realized in the early universe, about the features of the primordial curvature power spectrum, and of course we can infer some properties of the BSM physics that might play an important role in the very first stages of the cosmic evolution. Now I'm switching to my second part of this talk, where I will present my research results, the models that I have built together with my collaborators, our understandings and findings. So I'm starting with inflation. So these are some works that I've done with collaborators from the National Technical University of Athens and University of Athens the last 4 years. So the motivation to start inflation is what I said in the introduction, is that CMB give us information about very large scales, and we know nearly nothing about what happens at scales smaller than 1 inverse megaparsec. So there are many orders of magnitude of scales that we have no information about the dynamics of inflation and of course about the form of the power spectrum. So it's possible that the spectrum of primordial density perturbations is not flat as we see at the CMB scales, but it evolves. And the reason might be some new physics that might interfere at large k, at large momenta. And in the inflationary framework, if we see a deviation from a scale invariant, nearly scale invariant power spectrum, this means that we have a departure from slow roll. And the reasons for such a departure can be the presence of inflection points in the inflationary potential, or sharp steps or sharp turns. Here in this slide I saw an inflection point. Here we have deformed the alpha tractor model originally proposed by Lind and Kalos, and we have found that we can have a large enhancement of the power spectrum that can also trigger primordial black hole formation. Later on, we studied together with a group of University of Athens a different scenario where you have departure from slow roll because of a small step transition in the inflationary potential. And this is qualitatively and quantitatively different compared to the inflection point. And the resulting power spectrum that we get of primordial curvature perturbation is much different, and the most striking feature is that we have an oscillatory pattern around the peak, and I think this is also the smoking gun of this sharp transition. And it's exciting that this oscillatory pattern is can be seen at the gravitational waves induced by this enhancement of the power spectrum. So in principle, such a feature might be detectable and observable. Also last year, we built another model that could predict deviations from a scale invariant spectrum. And now this model has been built in the framework of multi-field inflation. And in order now to compute the spectrum, you have to take into account the new dimensions, the new directions that play a role in the inflationary evolution. And we have to solve this coupled system of equation with curvature perturbations and isocurvature perturbations. They're also so-called entropy perturbations. And we find that the spectrum also has a different shape. So we find different patterns for the spectra of density perturbations and tensor perturbations. And here in the middle you see a potential that now is under construction, let's say, with the group here in the University of Athens. Let me say that in order to compute the the spectrum of the curvature perturbation, you have to do it numerically solving the exact Mukano-Sasaki equation. Any other approximation fails. So apart from the inflaton field, there might be extra field that might have played a critical role in the early universe. And these fields are the so-called gravitational interactive fields that I described in the introduction. So a good framework to study these fields is together with dark matter. And the reason is that dark matter has a Rayleigh abundance that is very well determined by observation. So studying the system of fields together, we can learn information, we can extract information for both of these sectors. So here I will discuss the gravitational dark matter, which is a supersymmetric dark matter, hypothetical dark matter particle. Supersymmetry, of course, has not been discovered in LHC, but it might exist at higher scales, for example at TV scales or larger scales. But increasing the scale of SUSY breaking has a direct implication to the dark matter abundance because it increases the mass. So for example, in order for the gravitino to have the correct Rayleigh abundance, we must change the early universe cosmology. And the best way to do it is by introducing a gravitational interacting field that is actually motivated by many scenarios, for example, stringy setups or supersymmetry breaking schemes. And together with a collaborator from Japan, 5 years ago, we found that this cosmological scenario is detectable at the CMD sky because it has an observable gravitational effect. It changes the expansion rate of the universe, and this change is imprinted at the values of the spectral index and the tensor to scalar ratio, as you see here. In particular, we studied the supergravity R-squared model, and our I think basic conclusion was that given the value of the measured value of the spectral index, that I should say here that the fourth generation CMB probes can constrain the value at the per mile level, so with a great accuracy. So given that the measured value of the spectral index, we can say whether this scenario was realized or not. So we can say whether there is a desert beyond the electroweak scale, or there are new fields and new interactions that have modified the early universe evolution. So the same study can be done also in frameworks without supersymmetry, and this is what we've done together with collaborators from the University of Athens and from abroad this last year, in this work which is going to be published the next weeks. So we studied this new model where we have a new exotic particle that is unstable and decays with a CP violating manner, and can generate the baryon asymmetry, actually lepton asymmetry, that later is translated to baryon asymmetry via the Spalleron process, and the dark matter as well. So we have a simultaneously generation of dark matter in baryogenesis. And we find that our dark matter must be, in order this model to work, must have a mass of few keV. So here in this plot you see the three fluid evolution. So we have also an extra field that interacts gravitationally and modifies the thermal evolution of the universe. So when we have this coupled system of three fluids, this model works much better. And these are our results. So here you might see the values, the n star, which is the Effort's number of inflation, and here lambda is the scale of our higher dimensional operators. So this is the separation scale, and you see that there is a very interesting interface between cosmology and particle physics. So you see here an inflationary observable, which are the number of Efforts, and here is a scale. A cutoff scale of our theory, and examining particular inflationary models, for example hilltop, inverse hilltop, large fields, small fields, whatever, we can find which model is best matches in the best way with our construction. So I think this is very interesting because we expect that the precision will increase the following years, and will be possible to figure out different inflationary models, and therefore also to learn about the reheating temperature of the universe, and if there was departure from thermal equilibrium, and if there was a late entropy production and so on. So we can test all these scenarios, and I think this is a very interesting way to test physics beyond the standard model. What is exciting with this hypothetical non-thermal phase of the early universe is that it will impact not only the CMB observables, but we expect to produce a sizable amount of gravitational radiation, and we expect so because you don't have pressure, and the perturbations will start growing, and this growth will be anisotropic because you don't have pressure, and therefore you will have a non-zero quadrupole tensor for these inhomogeneities that will produce gravitational radiation. So together with Chris Kouvaris, we studied this scenario, and we computed the gravitational wave signal, and actually we derived this formula. This is a new expression that we give the amplitude of the gravitational waves that depends on how the quadrupole changes, and also depends on the PDF, probability density function, that gives the probability that a given configuration with some deviation from sphericity can be realized. So these are our results in these plots. So in the left plot you see the gravitational waves coming from Hubble particles from horizon that collapsed into black holes, and you see that this is a very small amplitude. So the signal is very weak. On the other hand, if you take into account all the Hubble particles, all the regions in the universe that the perturbations have grown, you find a much stronger gravitational wave signal. And moreover, you can find which is the reheating temperature of the universe, because you have the change of the frequency, but where the peak is placed. And the last year we took a big step further, and we studied the full evolution of the system using n-body numerical codes, because our analysis in the previous work has been analytical, and we cannot go in the non-perturbative regime, despite we could use some tools, for example the Zeldovich approximation, but it was impossible to study the so-called virialization process. So we've done so using n-body numerical codes, and we found the characteristic peak structure that's associated with the virialization process. And also we found that the structure of the peak is shaped in such a way that can determine the duration of the non-thermal phase. So as you see here in the simulation, you see a pancake collapse, and then a violent relaxation process that leads to virialization. And at some point, the gravitational waves, the gravitational radiation stops, because you have a spherical configuration that does not emit gravitational waves. So we ran about 10,000 times this simulation of cold collapse, and carry out also the data analysis. And we calculated the final gravitational wave signal that is given in this plot. And as you see, there is a characteristic pattern of the peaks that give us information about this hypothetical non-thermal phase that might have occurred in the early universe. I should mention here that we have used the computer cluster of National Technical University of Athens. Let me say a few words about my last project that has to do with dark matter and neutron stars, and this is a very interesting interface between particles and gravity. neutron stars are objects with very strong gravitational field that don't have a horizon, so we can see what's happening there. And they accrete dark matter. And the interesting thing is that in the center of neutron stars, there is a high density of dark matter. It might have signal there, coming, for example, from dark matter annihilation. Or we can study other scenarios with asymmetric dark matter, where we don't have dark matter annihilation, but we might have a dark photon that can be produced and decay outside the neutron star. So here is a Lagrangian of a minimal extension of the standard model that can accommodate that scenario. So together with Kuvaris, we study the implications of this scenario, and we hope to find some new interesting constraints soon. So here are my conclusions and the outlook of this talk. And my closing words are that there is an exciting and growing interface between elementary particles and gravity. And in the absence of direct evidence of new physics coming from collider experiments, astroparticles and cosmology can provide us the strongest, of course, indirect evidence for new particles interactions at energy scales that can be complementary to those of terrestrial experiments. And I think this is very, very exciting for today and the future. Thank you. Ευχαριστώ πολύ.